Let's continue our discussion next with example 2. So here you see a number of functions of the type that you normally see in calculus. A plane curve, a space curve, a real valued function of two real variables, a real valued function of three real variables, a vector field in the plane, and many other such functions are there that we normally consider in calculus. And each type of function has an associated definition of continuity for it. The general topological definition that we defined includes all these definitions inside of it. That is, they are all special cases of the general definition, and this fact will be clear once we prove general theorems on continuous functions on product spaces and metric spaces. Those things will come. But let's now move on next with example 3. You define this function f, which actually is just the identity function from the set of real numbers into itself, but the topologies are different because here we are not merely considering sets but rather topological spaces. In the first space, the domain space, the topology is the standard topology, whereas here this is the lower limit topology. Then what can we say about the continuity of this function? F is not continuous in spite of the function being the identity function. That is because here we have a different topology than the usual topology. And this is the reason. You consider this closed open interval 0, 1. It is open in the lower limit topology because it's in fact a basis element for the lower limit topology. But its inverse image under F, which is itself, is of course not open in R in the usual topology. You do understand the reason for this being equal to this because f is after all the identity function, so nothing changes. So you see that just changing the topology of any one of these two spaces actually has a drastic effect on the continuity, in spite of the function being the usual identity function, which normally is continuous if we are considering the usual topology on both the spaces. But changing the topology changes the thing entirely. Now what will happen if we interchange these two spaces and keep the rule for the function the same? That is, we define another function g, this time from RL into R, such that g of x is equal to x. Then what will happen to this? Is this continuous? Yes, it is continuous. For any open interval a, b in R, which is also open in the usual topology on R, the inverse image of a, b under G, which is a, b itself, this time this is open in RL, and that's why G is continuous. Now just like in analysis in topology also, continuity has several equivalent formulations, and this next theorem is about that. Let x and y be two topological spaces and f be a function from x into y. Then the following statements are equivalent. You see 1, 2 and 3 here, there is a fourth one also, I will write that. Let's first see what these are. The first statement is f is continuous. The second one says that for any subset A of x, the f image of the closure of A is a subset of the closure of f of A. This one. The third one says that for any closed set B in the range space, the inverse image of B under F is closed in the domain space X. So this is just like the definition of continuity, except for openness, here you have closedness. And next let's see number 4. So this is number 4. For each point X in the domain space X and each neighborhood, NBD means neighborhood, V of f of x, this V is open in Y, okay, in the range space. For these things, there exists the neighborhood U of that point X. U is a neighborhood of X means U is open in the domain space X, such that f of U is contained in V. If this condition is true for a function f and a given point x, then we say that f is continuous at that point x. Recall that we have so far seen the definition of a function being continuous entirely. But this is the definition, topological definition of continuity of a function at a point. So this theorem is saying, it's asserting that these four statements are equivalent to one another. If any one of them is true, then the other three will also be true. And now we are going to see the proof. The proof starts by first showing that 1 implies 2. So that means here we are assuming that 1 is true. So let f be continuous. Now we need to prove 2. So we take a subset, any subset A of x. Now what does 2 say? 2 says that then f of A closure is a subset of the closure of f of A. So let x be any element in A closure and let V be any neighborhood of f of x. You may get confused seeing so many assumptions. These lets are assumptions, right? Let. But first we set up the situation and then we see what we get out of that. So what did we take here? V is any neighborhood of f of x. Where is f of x? F of x is a point in the range space y. V being a neighborhood of f of x means what? That V is an open set in y which contains f of x. Because V is open and because f is continuous, so by the definition of continuity, f inverse of V is open in x. So this is something we are getting then as a consequence. But then what shall we get next? Next we have this as well. Since f of x belongs to V, how? Well, that comes from the choice of V. V is a neighborhood of f of x. So obviously this point will be in V. Because of this and by the definition of inverse image, x will then belong to f inverse of V. Now do you see something, some link here between these things, these ingredients? F inverse of V is an open set, okay, and it contains x. So that means it becomes a neighborhood of x. And x originally comes from where? X comes from A closure. This is a neighborhood of x and x is a point in A closure. What does that mean? X being a point in A closure means x is an adherent point of the set A. So from a previous result on closures of sets, every neighborhood of x has to intersect A at some point. In particular, this is a neighborhood of x because it is open and it contains x. So this one also has to intersect A. So there will exist a point, say y, in this intersection. And this implies that f of y belongs to f of A intersection V. How? Because y is in A, f of y obviously is in f of A. And at the same time, y belongs to f inverse of V. So by the definition of inverse image, f of y will belong to V. So that's how this is coming. And that's why f of x belongs to the closure of f of A. Where is this coming from now? What is V? V is any neighborhood of f of x, obviously in the space, range space y. For any such neighborhood, you have shown that the neighborhood intersects this set f of A, which is also a subset of the ring. So by that same result, which you used here, combining these two things, by that same result, f of x will be an adherent point of f of A. So from there this is coming, that f of x belongs to the closure of f of A. Now we chose x from where? X was any point in A closure. And we have proved that f of x belongs to the closure of f of A. So for this general nature of the point x as any point in A closure, f of x becomes any point in f of A closure, and any such f of x belongs to this. So that means this is a subset of this. This is what we wanted to show. So we have proved that 1 implies 2. Next we prove 2 implies 3. So we assume the statement in 2, that is, let this containment be true for any subset A of x. Now what does 3 say? 3 says that the inverse image of every closed set in y under our function is closed in x. So let V be a closed set in y. and then its inverse image under f is this, which we have given a name, so we call it A. You can understand why the author has written A here, because now with this A we are going to apply this. Now before we do anything else, let's see this easy consequence of this equation. What will happen if we take the f image of the sets on both sides? This will become f of A, this becomes f of f inverse of B. Now you go back to your section on functions, and from there you see that we have this containment in general for any function. F of f inverse of B is a subset of B. Now for any x in A closure, f of x obviously will belong to f of A closure, and don't forget our A is this A, okay. But from our hypothesis, this f of A closure is the subset of the closure of f of A. However, what do we find from this part? That f of A is a subset of B. So closure of f of A is a subset of closure of B. It's a simple thing, okay. Actually we have seen this before. If x is a subset of y in a topological space, then closure of x is a subset of closure of y. But what is B? B is a closed set in Y, so closure of B is equal to B. So we have now got that f of x belongs to B, and that's why x belongs to f inverse of B, which is nothing but A. So what have we got here? Any point in A closure is in A, so that means A closure is a subset of A. But we already know that A is a subset of A closure. This is always true for any subset, and that is why the two are equal. But that just means that A is closed, or in other words, f inverse of B is closed, which is what 3 states. So we have now also proved that 2 implies 3. Next we prove 3 implies 1. So we assume 3, which means that let f inverse of B be closed for every closed set B in Y. Proving 1 means proving that f is continuous. And that's why we need to take an open set, say V in Y. Now our aim is to prove that f inverse of V is then open in X. Write B equal to Y difference V. That means we are now considering the complement of this open set V in Y, and we are giving it a name, say B. Because V is open in Y, so B will be closed in Y, and so by the hypothesis f inverse of B will be closed in X. Now if we manipulate f inverse of B a little bit, it takes on this form. Let's see how. What is B? B is Y difference V, and we are looking at the inverse image of that under F, because inverse images of functions behave well with everything, union, intersection, difference. So it just becomes equal to f inverse of Y difference f inverse of V. This of course is X. Let me not elaborate any more than this, okay. These are just some simple function theoretic things. This is X, so we get X difference f inverse of V. This is closed in X, that means this complement is closed in X, so this is open in X. In other words, you have ended up showing that for any open set V in Y, f inverse of V is open in X, and that's just continuity. So f is continuous. So that means you have also proved now that 3 implies 1. So we have proved that 1 implies 2, 2 implies 3, and 3 implies 1. So that means 1, 2 and 3 are equivalent to one another. Now next we turn to 4, and let's first show that 1 implies 4. The strategy is this: we will prove this and its converse, that is 4 implies 1, so 4 will also be incorporated. So what is 1? 1 means f is continuous, so we are assuming that. What does 4 say? 4 say that if we take any point x in X and we consider any neighborhood V of f of x, then there exists a neighborhood u of f of x such that f of u is contained in V. So this is our setup. Now we have to find such a neighborhood u of x. And that neighborhood is nothing but f inverse of v. Let's see how. What does it mean for v to be a neighborhood of f of x? One thing is that it means f of x belongs to v. So by the definition of inverse image, x belongs to f inverse of v. So this set at least contains the point x. But is it open also? Yes, it is open. V is open in y and f is continuous. So by definition of continuity, f inverse of v is also open in x and it contains small x. So that is why it is a neighborhood of x. Let's give it a name u. And also the main thing about this set is that f of u is f of this, which as we have already seen in another thing, similar thing, this is contained in v. So this is what 4 states. So you have proved 1 implies 4. Now we just have to prove that 4 implies 1. So next 4 implies 1. I have started like this, assume 4, because you can already see the statement 4 in your book, so I did not waste time writing it again. Now we need to prove 1, that means we need to prove that f is continuous. So for that we have chosen any open set v in y. We now need to show that f inverse of v is open in x. Now let x be any point in f inverse of v. We need to prove that f inverse of v is open, so we have taken a point, any point. Then f of x belongs to v, so that makes v what? V is already open and now it contains f of x, so v becomes a neighborhood of f of x. And that is why by statement 4, there exists a neighborhood ux of x. This is an open set containing x and it's open in the domain space x, such that its f image is contained in v. So that means this is, we have applied 4 here. And to show the dependence of this open set on the point x, we have written u suffix x, because this point x can change also. You have taken x, someone else can take some other point. To distinguish those corresponding open sets, here you write ux, that other guy, whoever chose that other point, he will write uy if say the other point is y. Thus ux will be contained in f inverse of v. If f of ux is contained in v, then obviously we will get this. In other words, for any such x, this ux is a subset of f inverse of v. Now what happens if you vary x? Say you consider all the points x in f inverse of v. For each one of them, you will get one ux which is contained in this. So their union of course is also contained in this. Do you see how I have written this union? Union of ux as x varies over this. This set is contained in this. But the reverse containment is also true, which actually is much easier to see. You take any point y in f inverse of v. What can you say about the relationship between y and uy? Uy is after all a neighborhood of y, so it will contain y. Uy, however, itself is of course contained in this union. It's actually one of these sets, ux. So that's why any point here is also here. So this is also a subset of this, as much as this is a subset of this. So the two are now equal. Hence equality. Now what's the benefit of this? The benefit is that you look at these sets ux. What are these? Ux is a neighborhood of x. So being a neighborhood, it's basically an open set. So you are looking at an arbitrary, it's not exactly arbitrary, it will depend on how large this set f inverse of v is, but it's just a union of some open sets. So it should also be open. So that means f inverse of v is open. So we started by taking V any open set in Y, and we have proved that its inverse image under F is open in X. So that means F is continuous. So this is your 1. So 4 also implies 1. So now let's also, before we end this, let's also see how the structure of these statements looks. By structure of the statements, I actually wanted to mean structure of the proof. So if you look at the way the proof flowed, you get this graph, or you can call it a diagram because these are directed edges. So we go from 1 to 2, and then we went from 2 to 3, and then from 3 to 1. Also we can go from 1 to 4, and we can come back from 4 to 1. So this structure tells you that no matter what your statement is, which you are assuming to be true, you can reach the other statements via this diagram or digraph. Say your statement is 4, you assume that 4 is true, then 1 is also true, and that is why 2 is true, that is why 3 is also true. If your statement is say 2, you are assuming 2 to be true, then 3 is also true, and that is why 1 is true, that is why 4 is true. So like that, they are all equivalent to one another.